We can start recording. Everybody, welcome to the 26th edition of Cassandra Lunch. That's 6 months, actually. That's quite a feat. I think we're on a roll here. If everybody can see my screen and can hear me, just say that in the chat. I just need a couple of folks. Make sure that I'm not talking to mute or that I'm not sharing my screen. Okay, great. Today's topic is something that I think we can probably revisit again and again is basically, what are the things to look for when we're troubleshooting Cassandra in the logs. And the logs are the ledger which shows what's happening in Cassandra. It's actually a really good use case for people to see why you should have good logging in any software, let alone a distributed system in which there's multiple moving parts. I want to thank Akri for helping co-organize this event. If you're interested in helping or speaking or whatever, please reach out to him or me. But I'd love to have a co-organizer who can get speakers, sponsors, and if you want to be a regular speaker on this, I think just have to pick one focus and we can schedule you out for the next year probably. There's a lot of stuff to talk about Cassandra. We are part of a much bigger community. We are incubated in the data community DC, even though we are, simulcasting technically to Chicago and the DC Meetup. Data community DC is a diverse group, always looking for speakers from various backgrounds. We're part, as you can see, of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 more meetups than us. We cover data stacks, Cassandra, any variant of Cassandra, anything that talks to Cassandra, like Spark, Kafka, other technologies like Flink. Maybe serverless functions would be a topic. We don't have any new folks, but otherwise we've asked you to introduce yourself. Group rules, if you have a question, just ask, be polite, and let us know if you've seen something that you can share with us if you've seen something related to the topic today. DataStax is a sponsor and a partner, and so is George Washington University's Master's in Business Analytics. And we have some local sponsors in DC and Chicago. Institutional or organizational sponsors actually fund the nonprofit known as Data Community DC, which allows us to organize, I would say, close to 25,000 people in just the DC area and throw events for them. Any announcements? Okay. We have these videos recorded and uploaded to YouTube on a weekly basis. We can always go there and check out previous topics. Our website, Cassandra.Link, is in constant development, and some of these features you see here are actually different now, but this is a resource for anybody that wants to find the most authoritative articles, videos on Cassandra, and it's continuously growing on a weekly basis. I want to mention this is hand curated. All the resources that you can search are hand curated. No main upcoming events from our end. DataStax will be actually, we'll be doing a workshop with DataStax. I believe it is next week. I have to double check, but it's a talk on, in a series of talks called Event-Driven Toolkit. And we started out with Cassandra, making an API on top of it. Then we introduced Kafka and used Kafka to make that API event-driven. And then finally, this is going to be on Spark, which is how to now leverage Spark in that ecosystem. What would it be useful for? How can we consume messages with Spark streaming and or use Spark for doing some computation as the data is coming in? All right. So as you can see, we've talked about a bunch of stuff. And the last talk we did was on use cases in terms of reference architectures. Today's session is troubleshooting, standard troubleshooting logs. And there's different logs in Cassandra, so I'm not going to list them out here. But the structure for today is we're going to look at why would Cassandra have problems. We have talked about things like tombstones and white partitions before. We're going to lightly touch upon it. Then we're going to go deeper into what are the log messages to look for if things are not working well. And then I have some references, which when we post this to the website, you'll be able to go deeper, but we'll take a look at some of the references as well. So, generally speaking, folks who are new to Cassandra, they work on, let's say, one node cluster and everything is fine. And when things start to slow down and they start to see issues, what they'll do is they'll add more nodes and they'll basically they'll kick the can down the road in terms of solving some sort of problem. I'm not saying that's always the case. I just have seen 9 times out of 10 that certain problems that were happening in a one node cluster continue getting pushed all the way through to a 20 node cluster because nobody paid attention to the logs. And that's just the tip of the iceberg. And there's other things to take a look at as well. But the logs, they tell the truth. They tell the truth of what's happening in the system, what's working, what's not working. Frankly, you can just even count the number of entries per minute and see that histogram, and that will show you if there's something wrong with the cluster. So logs are very important. We did a session before where we had ingested the data into Elasticsearch and we looked at it. And I think a follow-up to this will be to take these and actually look for these errors. Unfortunately, unless the system has problems, we can't really show these. And I don't necessarily want to take a system that's running on a client environment and use that as a case study. So we have to see if we can make a problem happen on a test cluster. So what happens with Cassandra is that when you're in a one node cluster or when you're in a 20 node cluster, ultimately the strength of the cluster comes down to how it's handling disk. I'll also put here network. How it's handling disk, memory, CPU, and network. Network is rarely ever the issue. Although there are times where, for example, there's a failure, and when that happens, the network segment happens, you may have 2 different clusters that are not in sync. That's a different issue. Then there's the CPU, which is busy. It should be busy as much as possible. And if you're using data stacks, you have thread per core. If you're not using data stacks, you have Apache Cassandra. There's a point at which the CPU does well, and after that, it's not really going to help you much to have even more CPU, except if you use the same physical hardware to do multiple instances of Cassandra. So again, CPU is generally not an issue. It becomes an issue, but usually memory and disk are first when they come in. When a cluster is falling over, it's usually because it's a disk issue or it's a memory issue, which then causes the CPU to do more, and then that basically causes the node to fall over. Now, this is not unique to Cassandra. There are various different systems that have the same type of problems. Any high-speed distributed system, essentially it comes down to these type of problems. But the ones in Cassandra are actually pretty easy to diagnose and resolve. And so, let's talk a little bit about the system resources before we go dig deeper. One of the most common issues is data fills up and the system runs out of space. And basically, Cassandra falls over because it doesn't have any place to write data, or it doesn't have a place to write a commit log, or it doesn't have enough place, or if something is happening, there's not enough space to, let's say, do a heap dump, for example, and it just falls over. So when we think about the stability of the cluster, the first and most important thing to think about is the database, right? It's storing data. So take a look at the disk. And the disk ideally should be SSD, or on the instance itself, or it should be something like EBS. And both of these are very, very good. EBS on Amazon. But at the end of the day, a disk, if it's not fast, it's basically Cassandra's biggest first bottleneck. So what we end up doing is, to get the best throughput in Cassandra, is we separate the disk. So what we say is have a disk for just a separate disk for data, and then there's supporting data. And the reason I call it supporting data is that there's the word log here, but this is different from the log files, right? This is a commit log, and commit log is actually data. Commit log is where, as you know, when data comes into Cassandra, it first adds data to the mem table and simultaneously adds it to the commit log, so that if the node ever goes down and comes back up, if the mem tables weren't flushed to SS tables, it would have picked it up from the commit log, right? So it's important for your supporting data to have a place where it goes and is uninhibited. There are some other supporting data, but essentially commit logs are where data gets written in order to have durable writes. Hints, which used to be stored in the database itself, hints are essentially messages that the system is storing because another node is not able to take a mutation and take a write, so it stores a little message saying the next time this thing comes up, I'll send the message. We'll come back to that in a second. And then there's some saved caches on disk. These are not 100% important in terms of, like, if you were to lose all of your supporting data, you'd be probably okay, right? Unless it's super critical, then you definitely want to have a commit log. But if you have two disks, one with Cassandra data and another with commit log, both disks are simultaneously taking writes, right? And although this is a write-heavy workload right here, and the data is going to have both read and write, if you can separate supporting data, you're going to get better performance, okay? Again, we'll come back to these and why these are important. And then finally, there's log files. Now, log files, technically, you could put on either of these other disks. But again, anytime the system is running, anything that's happening in the system is also going to be writing to the log file. Now, this is not a super, critical or super high-speed need here. So technically, you could mount a drive and send the logs there. But it doesn't matter that much. It is important, however, that you have enough space for the log files. So first basic lesson in troubleshooting Cassandra is, do I have enough space for all of my things that I need to manage? The data, the supporting data, and the log files. And then there's also the heap dump, which would end up going elsewhere. You also have the temp drive, et cetera. But this is the easiest thing to solve. Make sure you have enough space. You can do this with whatever systems monitoring software that comes with your cloud or your network, they probably have some sort of scan that is looking at the disk space utilization. If you're not checking disk space utilization, check it. It's a really good preemptive step. It happens all the time. Oh, server is down. What happened? Ran out of disk space. And by the way, disk space fills up quicker than you can imagine, not because of a bad actor. It's just somebody imports a bunch of data, doesn't recognize that it's going to impact the system. All of a sudden, you don't have enough space for compactions. Compactions are when the SS table data is reorganized and made more efficient. Well, guess what? Cassandra can't compact unless it has literally twice the amount of data that you have. Okay, in ideal cases. And then the supporting data, it should be basically up to the amount of data. Right? There's a possibility that you could have enough data in your commit log that is equivalent to the size of the data that's being written. Okay. Memory, there's a lot of different tunings we can do in memory. That's a whole different, that's like 3 sessions we can talk about how to tune the garbage collection. But if you don't have enough memory, Cassandra's not going to work for you. Cassandra is a Java application. Java uses the heap. Heap is memory. There's also some off-heap memory that is used for things like, mem tables can be put into the off-heap memory, which is system memory, but it's basically managed by Java. It could also be the file system cache. It could be the partition key. I mean, there's so many different, the row cache, the key cache, so on and so forth. Memory can be a bottleneck, but there's a kind of a threshold at which if you have more memory, it can become a problem. And it ultimately comes down to garbage collection. You can have a lot of memory. And what that means is the garbage collection is going to take longer and longer and longer, and that could create pauses if you're using the JVM. It always becomes an issue where, not always, there's times where we've had customers that have very, very wide partitions, and they can't do anything about the data model. And the only way to resolve that issue is to add more memory. But the drawback is that they're going to have longer pauses, potentially. Again, it's a lesser of two evils. I mean, you're better off going and fixing the data model. But if you can't do it in a critical situation, adding memory will help. Memory issues don't always appear to you, clearly in the logs. And so we'll talk a little bit about that in terms of, why is memory a big issue and where can we kind of see memory contention. CPU is essentially how Cassandra is executing the 16 to 20 threads, right? It's doing the compaction, it's doing the repairs, if you're doing repairs, it's doing streaming, it's doing read requests, write requests, it's doing all of these different things in the different threads. So having enough CPU is important. Where CPU becomes utilized is when there's a lot of writes happening. One set of traffic coming in to write data ends up creating subsequent tasks for the system to do maintenance. So data comes in, goes to the commit log, goes to SS tables. Eventually, the mem tables, they fill up in memory. They have to be flushed. So the mem tables are flushed to SS tables. As SS tables start to grow, then the compactions need to kick in. So all of these things take CPU, right? So you can basically know when CPU is becoming used by looking at dstat or iostat to give you an understanding of how much time is being used by the user or the system, how much memory is being used. You can use top to see how much memory is being used. But CPU, you will know that why your CPU is getting used up more and more. Usually where there's lots of writes, right? It's a database. Data goes in. Lots of reads, right? More traffic coming in. And because of lots of writes, you have more compactions. And in the other cases, if you do repairs. Repairs take up a lot of resources. All right. every now and then you'll see a timeout from one node to the other. That timeout is probably not the network itself. It's probably because the CPU is busy. And the CPU is busy because it's capped out on memory, or it's waiting on operations to finish up at this level. All right. So we talked about system resources. How does Cassandra, basically use up system resources? We needed to talk about this first before we start to see what are the errors to look for, because frankly, Cassandra, if it has enough of these and it's tuned properly, it shouldn't give you any errors, right? If it has enough resources, it should be fine. Okay. Any questions about system use resources that are used in Cassandra? Okay. All right. So we're going to go, into these in a second. I wanted to first point out some references that you can take a look at. These are all going to be put up on the blog post once we're done recording. So a couple of things to note. DataStax has really good resources. Actually, I have it up here, where it tells you, how to figure out how much heap to allocate. All right. And it gives you some thresholds. Don't, for example, add, where did it go? I may not be here. It tells you, for example, don't put more than 32 gigs in the heap. Right? It's just not going to be useful, because the more memory you have, the more garbage collection time it takes. Here we go. Right. As well as if you're using G1, you can have up to, let's say, 64 GB. All right. Another good resource is Cassandra documentation page. So this is the old Cassandra documentation page. There's a lot of work that's being done to improve the open source documentation. And actually, it looks like they updated it. This is updated now. I have to show this. And when you look at log files, there's three main log files that we're looking at: system log, debug log, and GC log. GC log is not always enabled, or it is enabled, but it's not going to give you the information that you're looking for. So you have to go back and add some flags in order to get the data that you need. System log is the main ledger of what's happening, log of what's happening, and then the debug log goes deeper and gives you more information related to if there's a warning or an error. Common first thing to do, right, is look at the log for warn or error. You can use zgrep to look into the rotated logs that become zip files essentially, but this is a first step. Very, very, very first thing to do is to look at the log. In the debug log, you can also look for details of the compaction, and essentially you're able to find out, for example, how many times flushes are happening per key space. So this is getting into some fancy Unix cut, sort, and unique commands. But if you have Elasticsearch, or if you have Splunk, you can basically do the same type of things, which is to look for the frequency of certain messages. And then finally, the GC log kind of tells you what's happening, how long the garbage collection took. If you add more, which I don't think is here, but there's some settings to make it more verbose, it'll tell you things like how long the objects are staying in a particular stage. And, there's something in garbage collection called tenuring, as an object tenures between one stage to the next, how many times a particular object has tenured. And that can go deeper into, what you want to do with this information, which eventually maybe to add memory, add a node. We're talking about different aspects of Java. Java is a whole different ball game. There's a lot to learn in terms of tuning Java. I think myself included, there's a lot of folks who worked with Java for 20 plus years, and we're still continuously learning how can we optimize the garbage collection. Okay. So this is on Cassandra.apache.org. Great starting point to see what type of messages are happening, right? And there's an article specifically on this website that I wanted to show. This is not helpful. Let me get rid of this. So, essentially, these 3 logs are going to help you understand what's happening. Now, what is the problem that's happening? And to the end user or the developer, they don't necessarily know what the logs are saying, right? A lot of folks, they don't have their system logs uploaded to Splunk or Elasticsearch. What does the user see? The user sees, hey, the data is taking longer and longer to get, or data is showing me timeouts when I try to read or send the data, right? That's one. These slow nodes bring down the cluster. Well, what's happening on these slow nodes, right? If this is a degradation and over time the nodes start to come down, that's what the end users are seeing, right? Operations fail. So we call this, for example, drop mutation, or in terms of failed operations, if you can't write data or read data, or if you're not meeting local quorum, then that's a failed operation. And then finally, the read round trips, meaning when you're asking for data, you essentially you don't get a quorum, so you ask for it again, basically, if it's taking too many tries to get the data, then there's a problem. This is a very high-level explanation of what kind of problems happen. This is not an exhaustive problem list, but most of the time, the system that is using Cassandra, they don't care about the warnings. They don't care about the errors. Sorry, they don't care about what's happening in the logs. They care about getting access to the data that is stored inside Cassandra. If they can't access it, Cassandra's down, right? And sometimes that is because of underlying data model issues. Sometimes it's because of system contention issues. But how do you know what it is, right? How do you know to fix that? Well, these are, I would say, 7. I may come up with another one while we do this, but these are about 7 things that I look at the very, very beginning. After I see, okay, basically frequency, right? So I'll say that as frequency of log entries, right? That's very important. How many times is the system logging? If you have 10 nodes and one node is logging way more than the other nodes, there's something going on there, right? That's a very, very simple thing to look for. So how many log entries are coming into the system? How many log entries is each node doing at a particular minute or hour? This is a signal. This is a very big signal, right? Another thing to take a look at from in the log entries is the frequency of warn/error, right? It's kind of in the same boat here. That's what we just talked about. If you see a bunch of warnings and then the server went down, you should take a look at what those warnings are, right? If you see a bunch of errors happening and then the server went down, you should take a look at what's happening. And you know what? You can see the frequency across different nodes. So it may be that one node is apparently everything looks okay to it, but then all of the other 9 nodes are saying something is wrong. Well, then there's maybe a network issue. That one node basically thinks that everything is okay, but the other 9 say there's something wrong. Okay. All right. These are signals, and these signals point to a potential problem. They don't necessarily, they're symptoms, right? They're not necessarily the cause of the problem. And so, all right, sorry about that. These are just symptoms, and the symptoms don't necessarily, they're not the actual problem, but they can point us in the right direction. So, couple of things. Hinted handoff. Hinted handoff is a healthy thing. Hinted handoff means that when a node is not available, the other nodes say, I'm going to keep a message and I'm going to store it, right? So when we see hinted handoff, that itself is not a problem. But if we see a lot of hinted handoffs, that means that a node or a couple of nodes or many nodes are busier than normal, and for some reason, the hints are piling up and they need to be handed off all the time. So we see a lot of hinted handoff issues. That means that we need to take a look. Are we too busy as a cluster, right? Is the cluster appropriately sized? Do we have too much traffic? Okay. And hinted handoff is useful. But let's say you look at it and you say, you know what, this is fine. Sometimes we get more traffic. Sometimes nodes are busy. Not a big issue. The next thing related to hints that is an actual problem is hints are dropped. Now, hints don't drop unless a machine is down for 3 hours. That's a very big problem, right? Hints are being stored, and then if it's within the 3 hours, it'll get replayed if the node comes back up. But if the node doesn't come back up, then these hints are dropped. And telling you, if you see hints being dropped, that's a problem. That means some machine has been down for 3 hours. So what happened, right? How did a node go down for 3 hours? Right? That's a big problem. Related to hints dropped, I would say is drop mutation. And a drop mutation is basically data is, and these are metrics that you may, I said drop tasks, not just mutations. These are metrics that are stored inside GMX and can be accessible if you pull it into Prometheus or if you have Op Center. But just in the logs, you'll see messages dropped, right? Tasks dropped. And what that means is it's, okay, something is too busy. Maybe this node is too busy. Request drop, response, so this is important. So we got to ask here is, which nodes are dropping tasks, right? And just points to something else that may be going on, right? Repair errors are by the way, repair errors happen when repairs are running. If you're not running repair either through Reaper, Op Center, or yourself manually, then you don't have any repair errors. You may have some read repair messages, but essentially you're not going to see repairs. Repair errors come from a variety of different classes inside Cassandra. Look for things like anti-entropy, read repair, repair task, I think it's called. But what may be happening is it's unable to either look at the SS table or it's unable to talk to the other node to do that repair. Repair means synchronize and make sure that all the copies of the data, all the replicas of the data are in sync, right? Repair errors can also happen if the machine is too busy. Timeout. Connection timeout, request, write. There's a bunch of different things that could be timing out, and it just means network is not letting you do something, but the network is probably not letting you do something because of one of these. If you think about it, this is pretty much what the user will see, right? They'll see the timeout. They're not going to see any of this stuff, okay? They may get a notification saying that, hey, unable to meet quorum or whatever, but ultimately it'll come down to a timeout, okay? Wide partitions, the way we see them is the system says, warning, compacting large partition. And it'll tell you the table name, and it will tell you the partition key to look for that. And it's basically when the system is compacting data, it detects large partitions, and it'll tell you. If you're smart, you can put this all into Elk and Splunk and basically write queries to see what are my large partitions as they're, are they increasing? Are they decreasing? Did we solve the problem? Did the large partition warnings go away? Okay. When you're getting large partition warnings, it could be a signal that A, you're getting timeouts because the partitions are massive and you're hitting a memory issue. Or the partitions are getting worse and worse and worse, and your read timeouts may be increasing, or your delay in getting data, your latency may be increasing because of this. Another is for tombstones. Things like the actual log entry says, tombstone warn threshold has been reached, which is 1,000 tombstones. 1,000 tombstones means that all of those tombstones that mean this data is deleted have to be reconciled every time you read that partition. So similar to a wide partition, if you see a lot of tombstones, it usually is, it does correlate with high latency timeouts because it uses memory. It uses a lot of memory. And, infrequently, but every now and then you'll see out of memory error. Usually when you see this, you also see saving heap dump, and then the system just crashes, right? And you can go into the heap dump to see what's happening. Unfortunately, if you don't have enough disk space, the heap dump won't write. All you'll see in the last message is out of memory, heap dump failed, or something like that. Anytime you see, it's not just out of memory error, but anytime you see Java dot blah 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 blah, right? The stack trace. Any type of Java error will result in a stack trace. The system will continue. It's just that in that thread something basically didn't work or didn't happen. Exceptions, right? Exceptions are these type of messages are a clear red flag. Hey, something's not working. Okay. You will see the disk space issues. I don't know the exact language, but it's like disk full or something like that. Unable to write commit log. In fact, I don't think it's disk full. It's like, unable to write blah, 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 blah. Or you'll see corrupted, the word's corrupted, because let's say the commit log can't be written to. The next time you restart it, it says, hey, this commit log is corrupted. SS tables can't be written to. Next time it reads SS table, it says, hey, this looks like it's corrupted. And then finally, we have timeout. Okay. So what do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. In fact, what I'll do is I'll say these are 10. And by the way, it's the frequency of messages. You can look at any of these search queries in the logs, and you can say, what is the frequency? Right, what's happening? So holistically, each machine may be doing all of this. You can look at the frequency on each machine, but if you have many servers, you're going to have to look at every one of those machines. And if you don't have a log aggregation system in place, it's going to take a long time. So how do people do this generally? We actually have a talk on this that we've done before, but the general strategy is either online, right, real time, or offline. Generally, there's two ways to deal with logs. Online, you have Elk, Splunk, Datadog, Sematext, I think is another one, New Relic, right? They all have Sumo Logic, you name it. I was telling somebody that the reason all of these companies exist and more is because in distributed systems, you end up having to take a look at the data. And so these are just data analysis tools. So you basically have agents on all nodes. These nodes, they monitor the log directory, whatever, right? And gc.log you'll send over, debug.log you'll send over, and system.log you'll send over. And as the data accumulates in these systems, you can then do these queries that I was talking about earlier. Pretty straightforward. Offline, essentially what you end up doing is you, offline, you go to each node and you tar up or you zip up the log directory. It's not slash, by the way. This is wherever your Cassandra is installed, right? It's not /log per se. And then here, right? You compress it on each node, and this would include all of this. Oops. It would also include the rolled logs, right? .log, .1, .2, or if it's system.log, it'll be like system.1.log. I think it's system log 1.zip, and so on and so forth. Same thing with debug. Right? There's potentially there's a bunch of junk in there that if you haven't taken a look at it, probably should take a look at it. And you tar this up, and if you haven't done this in a while, this will be like 100 megabytes per machine, maybe even more. Maybe this is causing your disk to fail. You just have gigabytes of logs sitting around in there. You get it, right? And then you can go to another machine, bring it all together. So combine all of this, combine all the node data into one machine. And simple way is you open up, in one computer, and you do these searches on one computer via all, grep if you need to, or, ingest it manually into one of these, right? And why would you have to do this? For whatever institutional reason, somebody doesn't want to foot the bill. They don't want to deal with this. So you essentially have to bring up your own. And so, it's easier, I would say, just to say Elk, do this with Elk, Elastic, Logstash. Well, it doesn't have to be Logstash. It could be FileBeat, and Kibana. And because you can install, it's open source. All these things are open source. And you basically bring it all in. And if you, I'll send you a reference for our toolkit that allows FileBeat to dissect the time from the log file. Normally, FileBeat is just saving the timestamp based on when the file changed. But if you're doing offline, you need to get the time. And if you don't have it in a time series, then it's really hard to see what's happening. But those are pretty much your only choices. And I mean, I know that there's somebody out there that says, "Oh, you know what? We'll put it back into Cassandra and we'll run a Spark analysis on it, Spark job, whatever. Do whatever you want." But like honestly, a Lucene index Solar can also work. Elastic definitely works because it has all these UIs. It has Kibana to help you search for all this information. And if you have this in place, and you have, even if you have this in place, you can quickly just tar it up, ingest it, and take a look at it. Now, knowing what I know, if you don't do this, you're basically opening yourself up to operational risk. So if a system goes down, it'll take you 15, 20, 30 hour, whatever it needs to get all this stuff together, put it in a bag, and take it to the store, right? Get your shit together, right? get all your shit together, put it in a bag, and take it to the store, right? This is going to take you some time. But if you're constantly getting your shit together with, real-time log aggregation, immediately when a system goes down, you can go into the UI for Splunk or Elk or in Kibana and say, you know what, let's see the frequency of error messages. What does it look like? Oh, wait, looks like this one machine just started to have a bunch of warnings and it fell down. And then you can quickly go into, zoom in just on those, the data for that node in Kibana and identify exactly when the system went down. In fact, you can see when a system goes down, it stops producing log messages. Duh, right? You can immediately know what was the last message based on, the histogram of the log. So that's my big, tip is if you're troubleshooting and you don't have the right tools in place, it's a pain in the neck. I mean, just imagine having to open up the number of nodes. So let's say you have 6 nodes. You're going to have 6 different terminal sessions, and you're running parallel SSH commands to grep for these things. Come on, like the 1950s, man. So, anyways, this is again probably I would say first in a series of talks on troubleshooting, but hopefully this was useful. Specifically, I think this I have not seen one place where I have been told, hey, this is what you need to look for and why. So hopefully this is helpful to you. Okay. Any questions on what we just covered today? No questions. We are good. So actually, just as a quick, let me see if I have an Elk instance that we can look at. We do have an Elk instance we can take a look at. I'm bringing it up. And pretty sure the data has been scrubbed. Let me see. All right, so I'm going to say all time. All right, so here's Kibana, and I'm not going to go into the details of the log entries, but I just wanted to this kind of like show, essentially we're seeing in, this is the month of, I guess, February, all the way to September. We looked at a system and we analyzed the logs from February until this point. What that means is that when we zipped up the directories, all those logs were still there. We were lucky. And we noted that there was an incident that happened at this time and there was an incident that happened at this time, right? So this is just telling us the number of entries. It is not telling us anything else, just the number of entries. And we can already see that something bad happened here, right? That alone is intelligence right here. So let's go zoom in deeper. And this is on a slow machine, but if you have a real setup, you'll have more resources. So something happened on the way to the forum. Like we can see that something happened bad, or something started to happen, and then something really bad happened, and then bam. Okay. So if I wanted to look for warn, there's 659,000 errors, not errors. Let's just say there's 659 entries. But if you note, a lot of other stuff was happening. 609,000 more things happened, but 50,000 of them show us warnings. But it's in the same pattern. That's what's interesting. These warnings correlate with the number of messages that were there before. And so if I look for error, we're looking at the same time window, right? Hey, look at that. Errors also have the same general pattern. So this starts to tell us, help us tell a story that this happened, and then this happened, and then these things are correlated, and finally we ran out of memory. Remember we talked about exceptions, so let's take a look for exceptions. we're using wildcards, and as David knows, wildcards are expensive in Lucene. All right. So yeah, so the errors actually pretty much coincide with the actual, error, ERR, debug level. There's things that we're not parsing here, but if you make your dissector good, you can essentially identify the class, the line in the class. You could even identify specific numbers. So let's say, let's look for tombstone. Oh, new tombstone. That's really interesting. Wow. I'm impressed. This system did not have any tombstones. Actually, partition is a very common thing that you'll see, but here's a warning, right? Aggregation used without partition key. And all of a sudden, we know what happened. What we know is somebody did a scan and basically did not use, they did an aggregation query and did not use a partition key, which means that the system had to go to all of the servers and had to basically use as much resources as possible. And so probably what happened is this killed the server. It killed not only a server, it probably added a bunch of, made all the servers busy, and then one of them fell over. Okay. There's one more cool thing in here, which it's called time lion, and so what we're seeing here is a timeline of basically the most common things we saw. And this right here is plain text authentication. It tells us that somebody's trying to connect to the cluster without authentication information. Then here we go. Here's one that talks about flushing. There's one that talks about hard commits. So it's very important that you look at these errors in the context of the system you're on, right? I'm looking at something that may be completely different from some other system. Okay, and then as a quick toolkit that you can look for if you don't have this stuff, if you look for Cassandra Toolkit, you'll find it, but this toolkit essentially sets you up for success by showing you how to use these tools together, so FileBeat, Elasticsearch, and Kibana in the context of Cassandra. Okay? All right. And with that, I will wrap it up. Thanks, everybody. Appreciate you coming out. We'll be here next time, same time, same place, generally talking about Cassandra. Take it easy, guys.